In this model, we are going to compare and contrast the categorical model versus the linear model. First, the categorical model, also known as the logistics regression, it describes the relationship between a set of independent variables and a categorical dependent variable. And there are three types: the binary logistic regression, the ordinal logistic regression, and the nominal logistic regression. The binary is used to understand how the change in the independent variables are associated with the change in probabilities of an event, and it has two possible responses, like success or fail. And then the ordinal logistic regression models the relationship between a set of predictions and their response variables, and it has at least three groups with a natural order. And then the nominal models the relationship between a set of independent variables and nominal dependent variables, and it has three groups without a natural response. And then the linear regression model, it is also known as the ordinary least squares and linear least squares. We use it to understand the mean change in independent variable, and this type can also model curvatures. This regression estimates parameters by minimizing the sum of squared errors, and it is the most common model because of its simplicity. And in linear regression, we have advanced types of linear regression. There are the fitted line plots, the reg regression, the least absolute shrinking and selection operator regression, and then the partial least squares regression.
Some example models of logistic regression. And here I am specifically doing binary logistic regression. Here's my data set that I downloaded from online, survey data. So this survey data shows whether the customers are satisfied or not with the service they got. So the column satisfied and the column days to resolution are the two main columns that we're going to look at. And based on the days to resolution, we're going to see if the column days to resolution affects the result of whether the customers are satisfied or not. So we're going to use fit y by x. I casted the data set satisfied to y response, which is categorical data, and days to resolution to x factor, which is continuous data. So as I mentioned, what we are expecting to see from this model is whether the days to resolution really affect the customer satisfaction. And all the points above the blue line indicates that the customers are not satisfied with their service, and all the points below the blue line indicates that the customers are satisfied with the service. So if you look at the result, we can easily tell that the chances of the customer being unsatisfied when the resolution days are shorter is really low, which is 0.0001. So this means we can reject the null hypothesis.
So let's talk about the data types, specifically for continuous data. So if we're making a linear regression model, just the standard one, we want to use continuous data, and that means that the data is an actual number based on like actual data points versus categorical data, which could be like counts of different numbers of people in a certain category, or just any kind of integer that's not a continuous data type. Continuous data types would be like ounces of cereal in a cereal box, and those are the ones that we want to use if we're going to do this linear regression model. Here we have the different equations for the two types as given here, and specifically we want to look at this one, which is going to come up later in our linear regression model example. So let's go to that example right now. We have a set of data types that is about tire tread, and we have down here we have the data for different types of formulas, and these are different aspects of a tire that are influenced by these different factors here. And we can see we want to pinpoint this one hardness factor, that's like how tough the tire is, and we want to see which of these data right here, these inputs, the sulfur, the silane, or the silica, are going to most have a correlation or effect on the hardness. So we're going to put these inputs as our X factor, and we're going to see if there's a correlation to the hardness. Now let's see what that looks like when we plot it on a scatter plot. Here we have just the basic scatter, and you can kind of see like maybe there's something here, maybe there's a line that's going to be here, but we don't really know until we get down here and we add the fit line. And this is a line that's just going to go through the mean, and it's going to show visually that there might possibly be a correlation. And the additional adding of the confidence interval can better give an idea just in our minds at first glance. Here we have a very large confidence interval, which means that it's not as likely that there's some kind of correlation between the sulfur and the hardness of the tire. And here we can see that the confidence interval is a little bit thinner, so that means that we have more of a chance that there is something going on here. So let's keep this one in mind. And lastly, the silica, not very much. It seems very scattered. There's not much going on. We have a very wide confidence interval, which means we are not super certain that there's some kind of correlation here. Now I can look at the analysis of the data, and here's that equation again. We have the intercept, and then we have the slope and the one factor we're pinpointing. Here we have sulfur for silane and silica. What we want to look at is this R square right here. This is the number that's going to determine the extent to which the data points are correlated. And the higher it is, the more likely it is. Now none of these are super high, but we can see that the strongest correlation lies between the silane and the hardness. So this might be the factor we want to pinpoint if we want to change the hardness of the tire. We want to mess with this endpoint to affect that factor. And we can see here this probability is a different one from these ones, and essentially that's what we want to find out when we're doing a linear regression. We want to see the correlation.
Hi, this is Joey Gugliardi, and I'm going to be talking about the difference between the logistics regression and linear regression mathematical formulation. So for the linear regression, we see we have y equals b naught plus b1 times x1 plus b2 times x2 plus as many betas and x's as we want. And the goal of this equation is to find the parameters, or the betas, that minimize the sum of the square errors. So in order to determine accuracy with this method, we use a statistic called the root mean square error, and this is basically the standard deviation of the residuals, which is the prediction errors. So as we know with most distributions, the closer to one that the correlation coefficient is, the more correlated the data, the better the data. And so the more closer to 1 the correlation coefficient is, the closer the root mean square error should be to 0, meaning we have less errors in our data and better data. So the logistics regression, we have the equation on the left, p equals 1 over 1 plus e to the negative, essentially that exponent is the linear regression equation. This comes from the equation y equals the natural log of p over 1 minus p, where p is the probability of the presence of a certain characteristic. Therefore, 1 minus p would be the probability that that characteristic is not present. The goal of this equation is to find the best fitting model to describe the relationship between dichotomous characteristics. Dichotomous meaning of two categories. These are dependent variables and a set of independent variables. So we're fitting based on this. And it finds parameters that maximize the likelihood of observing the sample values. So we want to determine accuracy using this method, and a logistic regression is said to have a better fit to the data if it demonstrates improvement over a model with fewer predictors. It's performed by using a likelihood ratio test, where essentially it compares the likelihood of the data under the full model against the likelihood of the data under a model with fewer predictors, therefore better fitting the data. This is the difference. Thank you for listening.